I think we are live.
Yeah,
Double check.
I'll check. Yeah, we're live. Let's do it.
Apologies for the small delay, folks. Well, hello everyone. Welcome to today's episode of Corecast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome, everybody, to a brand new, exciting episode of Courtcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode. We'll get to it. So without further ado, let's get to it. So I guess Tim and Mikey, this is an interesting episode with a little bit of a twist in some sense when we were discussing this, and it centers on the a concept of entropy, and in particular, like around the second law of thermo and possibility of challenging it that we'll explore, which is that entropy keeps increasing. So I guess maybe to start things off, why don't we Mikey, could you explain to a complete layperson what is entropy? Like, how does a physicist think about entropy? And then Tim, can you explain like what's kind of the crux of this episode? Like, why is this important?
Okay, so I believe that you cannot violate the second law of thermodynamics, and Tim seems to think differently for some reason. So I don't really know where this is going to go. But okay, what is entropy? Um, so specifically, what is entropy? Entropy is like defined as the number of configurations that lead to the same macroscopic outcome. And that sounds super vague. I'm sorry. But what does it really mean? Like, so I guess intuitively, the way I think of entropy is like, imagine that you have like a chair, right? A chair has like, it's made of wood, right? And or potentially made out of wood. And in order to take a bunch of wood molecules um, and interpret it as a chair, those wood molecules need to be in a very specific configuration, right? They need to be arranged in the shape of like legs and a platform and a backrest, right? And the concept of entropy essentially asks the question is like, how can I rearrange? How many ways can I rearrange these wood molecules and still keep it a chair? Like if I take a wood molecule from the seat and exchange it with a wood molecule from the leg, then it's still a chair, right? So that's like a reasonable like I can exchange these two molecules and I still have a chair, right? But there's a certain way I can arrange the molecules so that it's no longer a chair, right? I can take a blender, I can put the chair in a blender, right, and just blend all of the molecules together, and then I will no longer have a chair, right? I'll just have a pile of like sawdust. So the idea of entropy is that the number of ways I can reconfigure the molecules of wood in a chair and still have it be a chair is limited, right? I only have a certain number of options, right? Like I have to be very careful about how I rearrange the molecules if I still want to keep this thing a chair. If I rearrange these molecules too haphazardly, it might no longer take the shape of a chair, right? It might just be like a pile of sawdust. And the idea is that a pile of sawdust has fewer features than a chair. So the number of ways I can rearrange the molecules of a pile of sawdust and have it still be a pile of sawdust is much greater than the number of ways that I can rearrange the molecules of a chair and still have it be a chair. Therefore, this pile of sawdust has a higher entropy than a chair because it cares less about the structure of the molecules. If that makes sense.
I guess historically, because of this fact, people associate entropy with disorder. They're saying that, and it's almost this anecdotal feeling that in order for something to be useful, it need to be more specific, like a chair.
Yes.
In order to yeah. So then and if you only care about burning the chair, you're gonna just burn it up, well, you don't care about the function that it has legs and a back, yeah, then you can grind it up, pile it up in any possible ways. In some sense, that when you burn up the wood, then the entropy increase. So there's this feeling that, I guess that's what the second law says. They make it more concrete in a technical way, that it says entropy always increases, and it has been almost one of the truest law that has ever been tested, I believe, by some metric, probably.
Yeah, and you're challenging it.
No, I'm not.
That's not a good idea. I don't think that's a good idea, champ. I don't think you should be challenging the second law of thermodynamics.
well, not me. I don't have the power to challenge the second law. I mean, I think there was a quote by some physicist that says, like, what, two things are inevitable, like the second laws of thermodynamics and taxes.
I would agree with only the first one, but
but anyway, politics aside, yeah. So I probably won't be able to challenge the second law, but it turns out that so this definition of entropy seems to be very technical, rearranging things and whatnot. But for those of us folks who have studied statistics, computer science, I'm sure people have heard of the phrase information entropy. On surface, this seems like totally different things. But it turns out that there's a deep connection between the two. And as we'll discuss, there's actually a way to sort of convert one to another, which is not obvious at all. And that's why, so this is the general lore of the crux of this episode, right? The second law of thermophysics deals with very, very large objects, like when you zoom out, yeah? But when you zoom in, things start to change. Particularly, we notice that when you zoom in on the molecular level, quantum physics becomes important. And also this description of entropy, which is a quantity that's only well-defined when you zoom out, becomes less and less well-defined. So it's a very reasonable thought to think that maybe if you zoom into the smallest scale where quantum physics becomes important, and as we'll see, when we really look at the details of a system using the quantum information, you might be able to break the second law of thermophysics.
Bold claim, very bold claim.
All right, let's jump into it. But I want to lay some background work before we jump into that. We mentioned, I guess, what entropy is. Tim, you mentioned information. Maybe before we jump into information, why was the concept of entropy even useful to begin with? Like, why was it why was it even defined, and like what was the purpose of it? Like, how did it help physics wise? Can we walk through a little bit of the history of that?
I think historically it has to do with like heat engines and whatnot.
Yeah.
The idea is that back in the days when people study physics, it's like when you study things like gases, like things that are burning, it's really hard to look at the details of system. Like historically, I think physicists have a feeling that you want to track every single molecule, calculate the equation of motions, and then study what happens, right? But it's very difficult if you let's say look at wood burn, because you can't track every molecules of the wood. So to bypass that, physicists come up with some quantity that doesn't immediately relate to things on a molecular level, but they pretend that a power wood is sort of they think about it statistically. Imagine a power wood is just some random stuff together. Then they're able to derive using statistics how much energy you can extract. For example, when you burn wood, how much warmth you can derive from it. And I think this is sort of the beginning of the consideration of entropy. It's a matter of simplifying your system by pretending that it is random in some ways.
So it's mostly useful from a thermodynamics point of view to explain essentially the randomness that people observed, or how can I what sort of, I just wanted to figure out the essence of what you said.
Yeah,
So I
I
guess
think
it's been
it.
mentioned, like, yeah, like, so this was first brought up, like, for very practical purposes, right? People were trying to build engines, right, and trying to figure out how they can extract energy from fuel. Let's say, like, if you
Mm.
have like gasoline or something, you can extract energy from that and make an engine run. You can do work with it. So yeah, historically the concept of entropy first came up in this context, right? Like in the
Mm.
context of like engines, like literally.
Yeah.
Um, and um,
I,
shoot.
I think I can give a pretty good analogy, right?
Okay.
Like like in some sense, back in the days, people are trying to build engines that can do more and more work. They're trying to move trains and whatnot. They want to move more goods with less input. They want to burn less coal to do the same work, right? And you can kind of think of that as kind of like a game you're playing. You're trying to maximize the work that gets done. And if you kind of relate this to gambling, like a game of poker, you can say, well, on average, how much money am I going to win, right? So physicists basically come up with this idea, hey, if you pretend that the system is random, on average, you're gonna win this amount of work. Yeah. And it seems that this
Mm.
approach is very fruitful. And it even works in today's car engines or like turbines and whatnot. If you pretend that
Mm.
the system is kind of like gambling or investing in the stock, if you like, on average, this is how much energy you're gonna get out of it, and you can't beat the dealer. The laws of thermophysics, it's like the laws of gambling against the dealer. Is you're just going to win or lose however much on average. You're never gonna come out ahead. Basically, this average trend turns out to be so powerful that it governs almost everything. If you think of system physics as kind of like a casino in Las Vegas, you know.
Mm. Gotcha.
Wait, but the most salient point of this second law of thermodynamics, right, is that like you can have you. Okay, so when I think of the second law of thermodynamics, I think when a lot of people think about it, like the upshot, right, is that you cannot get work for free, right? You cannot have a
Mm,
perpetual motion machine, um, because a specific configuration of particles is kind of like a resource. Like if I arrange like Legos in a very particular way and make it into some structure, I can think of that as like a resource, right? And like like if we look at gasoline, right? Like the fuel that we use to like run our cars, right? The energy is stored in a very, very particular configuration of molecules, right? Um,
Mm.
and once we expend the energy, that resource is used up, right? And we can't get it back. Because when we burn like a molecule of fuel, for example, it turns from a very structured molecule into a very unstructured molecule. And
Mm.
so like we kind of extract the energy from that, and
Mm.
now that energy is gone and we can't get it back. Um, so
I have a question kind of to challenge that. Like, I mean, the way I'm thinking about it is like you're trying to ask the question like how much useful work can I extract out of the system?
yeah.
And you say gasoline, like you have you put it in your car, it exhausts out into a more disordered structure, the
Yeah.
waste. But couldn't the waste of that be like a energy source or some kind of configuration that another thing can pull from, and then its waste could be like ours, sort of this like cycle?
No, yeah, you can't turn poop into energy.
yeah,
Like,
I think a good analogy. It's like poker game. Like basically, if you imagine, the all the molecules, it's like poker cards. Imagine you shuffle 10,000 deck of poker cards, right? And you randomly draw like 1,000 cards. You can ask how many aces are going to be in that card. You know, if you just randomly draw them, you're gonna get, I don't know, maybe you can calculate the statistics, which I don't know, right? Maybe like
452.
yeah, one out of 13, right? One out of 13 cards will be aces on average. It's gonna be statistically impossible for you to draw like 1,000 aces. Just not gonna happen. And basically extracting work out of poop is it's like drawing 50 aces out of like a random deck of like a bazillion random deck of cards, all shuffled up. That's just statistically totally impossible, right?
I see.
So this is it. Like you can't beat, like you can't do much with random deck of cards.
Wait, sorry, all this talk of poop is getting a little bit too big. For some reason, I keep thinking of dominoes. Tim, do you think dominoes is good? Like, so, like, everyone's seen this, right? Like, when people spend a lot of time carefully stacking dominoes together
Yeah.
so that they create, like, you tip one over and then everything goes, right? Um, when I think of the second law of thermodynamics, I always think of dominoes because the work you have to do to set up the dominoes in that very specific configuration to get that very specific, beautiful pattern where the dominoes like collide with each other and creates a chain reaction and goes down, right? Like you can imagine that as like doing some kind of work, right? Like you can imagine I take I take a lot of care and time to set up these dominoes in such a way that when I push one, I get this chain reaction, all this energetic stuff happens, right? But once all the dominoes are down, I can't do anything else after that, right? I can't like reverse the system and make all the dominoes go back to standing up so that I can get this again, right? Like that's a resource that is now lost.
Oh, I guess Tim, what were you going to respond or?
I mean, that's
Thought you were-
Yeah, Tim,
reasonable, but
explain entropy to me in terms of dominoes.
well, a good example is to me, entropy always sounds like some sort of exploitation. You know, like imagine you have a box of gas, and all the gas molecules on one side. Then of course the tendency is for the gas molecules to push out to the other side, right? And you're exploiting this fact in order to get some energy out of it. Just like I don't know, just like if you play poker, right? If all the aces are on top, let's say you're in cahoots with the dealer, you're gonna get all the aces. You know, you're gonna win. You're gonna win big, basically. So it's kind of like if the system is in a particular configuration, you can arrange an engine or some, in this case, an oven. Throw some coal in there, heat it up, then it's gonna do some work for you because it's in a particular position that you can exploit.
No, that makes a lot of sense. Um, yeah, no, that makes sense. So I want to move to I guess this concept in thermodynamics called Maxwell's demon, and kind of give a little brief overview, and then I guess Tim, I'll point to you to kind of expand on it. I guess the thought experiment comes from trying to challenge the second law of thermo, like can you reduce entropy, meaning the number of possible configurations of the system. So if you had like a bunch of, let's say, fast and slow moving part, or say not just you have a bunch of particles in a box, and then you have this like tiny little demon that's like sitting in the middle who has this like this slide door that they can open to let particles go in and then shut it very quickly. And the concept is they just keep watching all the particles and try to eventually move one particle from like one part of the box to the other and shut it. And then eventually, as soon as it's done, all the particles will be on one side of the box, and thus you have reduced entropy. So that's my understanding of it. I guess, Tim, do you want to expand further on that? Like, does that violate the second law of thermo? Is there something, because I showed an example of it, entropy going down in this
Yeah,
case?
yeah. I think this was one of the thought experiment that people came up with, right? So a system that you can no longer extract any work is said to be in equilibrium.
Right.
That means there's not much more you can do to it, and it's at maximum entropy. Let's say it's all mixed up. There's not much you can do, like a deck of cards that's completely shuffled, you know.
Mhm.
But the idea of the Maxwell demon, it's sort of like imagine you're like if you can see the cards that are underneath, right? If you can know which molecules are moving faster than others, you can follow them and put a piston right in front of them so that they push the engine. Yeah. So initially people were confused because they realized they thought that the second laws of thermodynamics seems inevitable, like you can't beat it, at least statistically. But then there was a resolution actually. Physicists realized that so this process is it's possible potentially. If you have really fast electronics, you can track the molecules. You could just follow them, right? But I forgot which physicist. My crediting is probably terrible. I don't know which physicist came up with this, but people discovered that in order for you to have knowledge on which particle is where, you need to store that information somewhere and then be able to act on it. But then, in order to do that, you need to expend energy. So people realize that even you can use this way to reverse the increase of entropy, but you have to do it at a cost by injecting more entropy somewhere else, because you gotta run a little computer to keep track of where the molecules are. So it seems like, at least immediately, the second law isn't completely challenged yet. It can be, it's still okay because, and this is kind of the critical link, right? Now this is where people find out, hey, look, information is actually linked to how mixed up something is. If you know more about the system, maybe it's not as mixed up as you thought, basically.
I just want to say, Mikey, you seem to have a very pleased look on your face that the second law of thermo has not been defeated yet. I saw you in anticipation, just like waiting. Oh, this is it.
No, I don't know.
Anyway, I want to. Okay, now we brought information in. So as part of my jargon alert, let's define what information is. And I mean, there's a colloquial definition of how people think about information, like, say like you're, spying or, doing some kind of reconnaissance operation. And I say, oh, like X, Y, and Z target is in this location here. I've given you information. But is that the same way physicists think about the word information, or is it different? Like, how do I think about this? Either Tim or Mike.
I think it's related, right? Like if you flip a coin and the coin it's heads or tails.
Reduction of uncertainty. Yeah. Reduction of uncertainty is knowledge.
Yeah. So
reduction of uncertainty is knowledge. That's yeah. I think Tim has a spiel to go on, but that would be just my gut instinct response. Is that knowledge is a reduction of uncertainty, right?
Yeah. I mean, we can be a little more specific, right? Like entropy is defined by the number of possibilities. Let's say I flip a coin; it can be heads or tails. There are two possibilities, right? The entropy is technically you take the logarithm, but whatever. Forget about that. Let's say there are two possibilities. In order for me to reduce it back to one possibility, the amount of knowledge I need to know corresponds to resolving this possibility. And in information, it's 1 bit or log of 2. So in some sense, information and entropy are sort of counting the same thing, but just slightly different perspective. Entropy is counting the number of possibilities. Information is sort of saying, well, how much possibility I have to consider or I have to know in order for me to know what's going on. So in that sense, it's actually sort of the same thing.
Hey, Tim, can I ask you a question, though? Like, do you think of entropy and information as kind of like opposite quantities? Like, just intuitively for me, because like entropy means that this disorder is increasing, it means that the uncertainty is increasing, and information, like at least in the layman sense, like we think about it as kind of the opposite, right? It's like when how does that work?
And indeed, I think this is a more modern viewpoint. If you think of it, entropy as in this modern way, the fact that entropy is increasing means that the information we have about the world is decreasing. So we have more and more uncertainty about the world. And it almost feels like you're losing control of the world. You know less and less and less. And this is sort of
I think that this goes back to the chair analogy, right? Like if I have a chair, then I know that I know that the molecules of this chair are in a specific configuration, right? Versus like if this chair is just a pile of sawdust, then now like sorry.
Yeah, the analogy works, right? Like, imagine I tossed the chair to the trash. It goes to a
Yeah.
incinerator, got burned up. Now the chairs are all over the world. Who knows? It might be in the upper atmosphere or in Antarctica. My knowledge
Yeah.
about where the chair is has drastically reduced. You
Yeah.
know.
And it's not just that your knowledge of the chair has been reduced, but like even the chair's knowledge of itself has been reduced, right? Because
But
yeah,
but it raises an interesting point. If you think instead of thinking about disorder, now you're framing it in terms of information. The question is, does that mean entropy is subjective?
Wait, before we jump into that, I just want
yeah,
to add a few points to clarify, to add more context from a computer science lens. So my understanding of entropy and information is they seem to be I've seen that basically are the same thing in some sense. Like entropy was discovered in statistical physics, information was discovered by a guy named Claude Shannon, rather defined, and has, I mean, other than the units, one being bits and other being nats or something based on logarithm, we don't need to get into those details. They're essentially the same exact formula. And so my understanding is entropy is the number of yes, no questions you need to ask in order to specify the state of the system. So if I give you a sand pile of of the chair, for instance, I need to ask more yes, no questions to determine like what state it's, because it's in a single state. Like at least, that's how I think about it. It's not, I mean, yes, you could like arrange things differently and get the same sand pile, but there's more ambiguity. So I need to ask more questions of it in order to determine what state is it in. Versus a chair, I need to ask less questions, like because it's more structured in some sense. And then I want to also make sure we're not confusing between knowledge, information, and then the concept of information gain, where if I ask a question, how much like uncertainty do I actually reduce? So could we expand upon that? Because I don't know if knowledge and information are the same thing. Like my understanding is that if you have more uncertainty, you have more information to gain in some sense by asking yes or no questions versus like a thing that has like only one possible state in one possible way and nothing else. Like there's no uncertainty about it. Kind of like I'm just thinking of an
like
example.
a unique configuration, right? Like
Like
Yes.
a very unique configuration that if I tell you this is the thing we're looking at, you know exactly what state it's in.
yeah.
So
And
I
if you
really
change any two things, then it won't be that thing anymore.
exactly. So I really want to clarify this because yeah, I just want to make sure there's no
Yeah,
confusion. So
yeah. I think the confusion came because historically people believe that entropy is sort of a quantity that is inherent in a system. This system just has this much entropy, and that's it.
mhm.
But the more modern viewpoint is that entropy is actually subjective. It depends on how much you know, right?
Mhm.
So in that sense, entropy is exactly the same thing as the information you have about the system, up to a negative sign, of course, right?
Mhm.
So a good example, a good thought experiment is this, right? Imagine you have a bunch of gas molecules in a box, and you talk to a physicist. You say, "Well, how much entropy is there?" He will tell you something. Entropy 5,
You can
right?
calculate it.
Right, you can
Right?
calculate it. Of course, you can calculate it. But imagine each molecule actually had a little label on it, right? And I
Mm.
tell you what that label is. Now, if I include that label, the entropy calculation will actually change. Like, imagine all the gas molecule in one side had one label, all the gas molecules on the other side had a different label.
Yeah, like you painted one red and you painted the other blue.
Right. If you can somehow do that, all of a sudden the entropy calculation has changed, but then the system hasn't changed. I just haven't
Yeah.
told the first physicists that there were labels, right? So you can kind of see like, hey, look, people used to think entropy is objective. It's just something inherent in the system. It's no longer true, and this gets even murky when you have quantum physics built in, because now with quantum physics, everything is inherently unknown, and where the system
Not
is
totally unknown. No, not totally
right,
unknown.
not totally unknown, not totally unknown,
Yeah,
right?
but there's something you can never know.
Right. So I think the more modern viewpoint is through the lens that you were describing, Sahil. That the entropy now has more and more of a computer science flavor,
Mm-hmm. I see. I see. Is it so I kind of want to touch upon what you said, like when you bring quantum mechanics, it becomes a bit murky. So one example I'm thinking about that comes to mind that definitely like to expand upon is like when I think about flipping a coin, classically speaking, it can either be heads or tails. So there's some unknown information. But let's just say in principle, I had this like really powerful computer and it just knew the exact initial conditions. Forget about chaos theory and all that stuff. Suppose it doesn't exist. I flip it and then I'll know exactly whether it land heads or tails. So there was no uncertainty in the process. It was completely deterministic. Can you explain how it shifts to quantum mechanics? Like, can I get a sufficiently powerful computer and like know things about a quantum system, or is that like is there a certain limit? There's like bare bones, even in principle, I can't like even if I improve the technology like light years ahead, and figuratively speaking. But yeah.
Yeah, the thing about quantum physics is that we have some episode in the past that describes some of that. But in a nutshell, quantum physics tells you that no matter your technology, if you have a quantum coin that you flip, you can try really hard to follow the air molecules or whatever. The best you can do is if you have a good quantum coin, it's 50-50. And why is that? I'll tell you the way I like to interpret it is through the multi-world interpretation. Basically, it tells you that there are many possible paths the world can take. There's one world in which it lands head, and in which case it will show up heads in a machine. And there is another path where it shows tails, and it shows tails in the machine. At any moment in time, we as humans are only privy to one version of it. So no matter how your technology improves, you'll never be able to jump to the other interpretation. And this is sort of the quantum irreducibleness of this randomness. Because we have one universe, we can only experience one possibility. So it doesn't matter how good you improve your technology. You just don't know which one you're gonna follow. Yeah. So this is the quantum nature of it. That in quantum physics, it's not about what you don't know. It's just that you cannot know it ever. And there just is possibilities. There are possible worlds where you would have measured the other way, but these are irreducible. So in that sense, entropy becomes more powerful. I don't know if that makes sense. Like possibilities are just inherent to the system.
Yeah, no, that totally makes sense. I mean, that definitely touches upon some previous episodes we've talked about where we've talked about the preservation of possibilities. So all the possibilities are there. We're just in like one part of the possibility space. And so it makes sense that if you build the technology in one part of the possibility space, you're not gonna be able to suddenly just jump to other possibilities, or the chances of you doing that are like exponentially suppressed.
Right. Yep.
That. So I guess I want to kind of come now we've explained information. I guess Tim, this is maybe you and I would disagree. Like I think information and entropy are the exact same, no minus sign, like exactly the same, or information gain. Like there's no negative sign at all. Maybe there's a negative sign somewhere else, but anyway, so I'm just gonna throw that out there. As being I guess the only form of controversy I can generate
I think my statement remains correct up to a negative sign.
Yeah.
This is
I guess absolute value of what we're talking about.
Absolute value.
Yeah.
Yes.
Okay. Anyway, so I want to jump to the main part of this episode, which is like this very interesting result. I'll let you expand on who was the guy who initially discovered, and what was it? The thing that Mikey seems very combative about. The second law of thermo cannot be violated.
It's not just me. I'm sure everyone listening would be very combative about this.
Well, let me just preface that. That's why the title of the episode is that it challenged. It didn't break it, okay? But challenging it did. I think it did legitimately challenge it.
Yeah, it's always good to reconsider the assumptions that you thought were true. I agree with that.
And this is a good idea in physics because
Mikey.
Sorry, yeah, I gotta go. My work's calling, but
okay. Yeah, no problem. We'll carry on.
Yeah, we'll continue. Okay, no worries.
I'll adopt Mikey's combativeness and
be the antagonist.
Nice. just trying to be nice, giving like, oh, it's good to hear this, but he doesn't he doesn't want to hear it.
No, he's too nice. But anyway, so there's this physicist Leo Szilard. I think during the Nazi regime, I think he's a Jewish physicist, left the Nazi regime. But what do I know? I don't know much about histories of science. But anyway, he came up with sort of a way to use this Maxwell demon idea to kind of beat the second law. I mean, the idea is simple, right? Like imagine roughly, so in order for Maxwell's demon to work, you have to know very precisely where the molecule is to open the trap door to let the fast molecule in. But he thought that, maybe you don't have to be precise. Like, for example, if you just can know, let's say on average, you know that the left half of a box has more molecules. So you can stick a divider there, then the divider will move to the right. And you just take the divider out and just wait until there's a little more gas in the left, and just continue to do that. Maybe you're able to extract some work. Yeah. And indeed, if you zoom in, because you're doing it on a molecular level now, you have to involve quantum physics. And it turns out that using quantum physics, you can kind of play with the system a little bit. You can kind of build these contingency plans. You can like entangle yourself with the system and be like, hey, look, if there are molecules on the left, you move the piston. You try to move the piston one way. If not, you align your piston the other way. And if you do that, you actually could get a little more work or energy out of an engine. So these are called Szilard engine. You actually get a little more energy out than you expect. And I think researcher recently, from a Quanta magazine article, that they've done that. They show that this is in principle possible, right? So that's the interesting bit.
I guess I want to appreciate the significance of this more. So is it like you actually be able to reduce entropy, or is it not enough to reduce? It's just that like the increase in entropy would be less than you think, or what? I'm trying to frame this in the context of entropy, like the perceived disorder of the system.
Right. Well, I mean, yeah. At the end of the day, because we talk about this loophole, right? In order for you to know something about the system, you need some processing power, and that will cost energy. So at the end of the day, it won't break the second law. But of course, the second law needs to be modified to take knowledge into account. But if you think about it, this is kind of weird. You were just talking about heat engines and whatnot. And somehow, if you have more knowledge about a system, somehow that matters, right? And it's a physical proof that entropy is sort of subjective. If you know more about the system, you're able to exploit more. So it sort of shows you that, hey, there's a little bit of a crack in the second law, and somehow we've almost come full circle, right? People were in the beginning trying to derive something fundamental about the universe through laws of thermodynamics, but now we realize that, hey, guess what? It actually has more to do with how much you know about the system. Somehow our knowledge gets involved. And that's interesting. That's weird. That's unexpected a little bit.
So how do I think about knowledge in this context? Like, is it like how? Yeah, I guess is it just like knowing the positions of I don't know if positions make sense because we're talking about quantum mechanics. Is it like knowing the state of the particles? Like, I don't know. How do I think about this?
Yeah, and I think you don't have to know about the state. In fact, in order for you to beat thermodynamics, you want to know just enough information to be dangerous. And I think a good analogy is kind of like the stock market, if for those folk, or a game of poker, if you like. The laws of thermodynamics just kind of tells you on average what your return will be. Like if you add up all the investors in the world, you know for sure they're just gonna do the average return. Or you add up all the gamblers together, they play games of poker. This is how much you make or lose. You can't escape that, right?
Yeah.
But now there's this using this quantum knowledge. You build these quantum machines that are able to exploit the knowledge. It's almost like, I don't know. It's like you have insider information. It's like you're doing insider trading. I don't know, Congress members or whatever, right? Like the game is rigged. It turns out that you could rig the game of physics, the game of thermodynamics. And that's kind of crazy. The games of quantum information, you can rig it in your favor, and you do a little bit better than the average.
Wait, so is there a limit to how far can I push this? Like, does this mean I could like come up with perpetual motion machines as Mikey was
Well,
mentioning that you can't?
yeah, perpetual motion machine definitely not, because like you need a computer to process this, right?
Okay.
But now it's weird now. Like for you to derive more energy, like if you're smarter about your computation, you could do it, right? But I don't think people know exactly what the limit is. That limit at the end of the day will be like a modified version of the second law. Like how much like basically the laws of thermophysics back in the days tells you something about the Carnot engine. I don't know if people who are familiar. It tells that for a very average system with some temperature, this is how much energy you can get out of it. You can't do much better. And this governs car engines, turbines, whatever. You can't do better than that. Boo-hoo. There's not much you can do. Well, but hey, if you look at a small enough system, it looks like you can kind of beat it. But of course, for sure, if you go back to the initial assumptions for these theorems, of course it violates them. This is not your average system. This is a system that you have a much more intimate knowledge of, right? But but once again, it's weird now because this connection between knowledge and entropy was somewhat unexpected, at least back in the days. Like Maxwell wouldn't have thought that you know more about the system, somehow you can win the game.
So okay, let me try to see if I can like understand this more. Okay, is it something where like just sort of thinking about this. So for a small system, you do better than you would expect. Is this kind of like if I could scale this approach, would I eventually like be able to like completely crush the second law of thermo? Like say it like, a sufficiently large, powerful quantum computer, and I was like really like it almost, infinitely intelligent in some sense. Like, could I do it?
Well, if I was one of those quantum computing startup, my answer will probably be yes, but but as a physicist, probably not. I would be surprised, but I wouldn't be surprised if you do a little better, and that the second law needs to be modified by taking information into account. But I also believe that this is the new era where physics and information theory and computer science kind of have a little bit of intersection. And especially when people did research on black hole physics, and why does black hole matter, you say? Well, because like what we talked about many episodes ago, black holes have entropy, they have information, and they're the ultimate scrambling machine. And people have proved that there are certain limits. There's certain computational limits in the universe. There are things that are so convoluted that you just won't be able to compute. And I don't doubt that one of the reasons second law is valid is because maybe if you make the system large enough, there are just certain limits in which you can never anticipate what the system is going to do enough for you to extract just infinite energy out of it. That's probably is true. But I don't think anyone know what that answer is. But it's interesting that, we've come full circle, right? Back in the days, people thought, oh, the entropy, somehow, increase of entropy is inevitable. Now, all of a sudden, in the modern physics, we realize that, hey, it's not so much about the disorder of a system. It's an old interpretation now. Now, it's really, there's limits of computation that things you cannot find out because of, you just couldn't come up with better algorithms. That's a little weird, isn't it?
I feel okay. So are you? I guess I'm just trying to understand this a bit more. Is it the case where I still am a little bit confused about the use of the word knowledge. Is when you talk about knowledge of the system, is it like a specific algorithm to compute something, or like what role does knowledge play in a quantum computing context?
Well, I would say knowledge here has more specifically things to do with measurement. Like you know what the system is doing. You know, like if somehow you can weight the molecules to know that it's a little heavy on the left side at this moment, and you can react fast enough to take advantage of it, then you can put a piston down and allow it to move. But you have to do it at the quantum level because this is like at the molecular at the molecular level, right?
Uh-huh.
So knowledge here is physical quantities, but then you have to act on it. You have to do something to
Yeah.
it. Yeah.
Is it where you'd like have to have because I'm thinking about this like if I were like a tiny little like quantum demon for lack of better words with like
Mm.
this computer and I had all these particles but really quantum mechanically speaking maybe waves or I don't really know how to conceptualize in my mind but we'll call them particles for lack of better words. Would I need to know like where to send a measurement to and then measure it and then figure out what to do with that like I guess knowledge that I've acquired and then figure out how to adjust the system or how does this work?
Yeah, so there's two components now. First, there's measurement, right? You have to know you have to have some reading of what the system is doing. Of course, measurement is never perfect. And then there's also anticipation. So maybe if you read that, hey, the system is flashing a green light, then you can do a calculation to be like, hey, I know that 3 seconds after the green light, there will be more air molecules on the left than the right. Let's say you can anticipate that. Then you're gold, right? So yes, there's the measurement aspect. There's the computational aspect. Can I use the measurement to compute something? And is there enough time for me to exploit that? I think all that will have to come together to make an efficient engine that exploit this process, the predictability, the measurability, what else? Yeah, and the information aspect, right? What information you have, can you use that to infer what it's going to do in the future, and can you make a reaction out of it?
I see. So it's essentially like I guess some degree of like more predictability, for lack of better words, and then how fast can you act on that, like, prediction
Right.
that you've
Yeah.
made.
Exactly. And I think in black hole physics, people do believe that there is a limit, right? Because we truly believe that when something goes in a black hole, there's a degree of irretrievability, like that thing, and we know that because black holes Hawking radiate, eventually the stuff that goes in the black hole disappears. So in previous episode we said that hey, maybe if you have an infinitely powerful computer, maybe you can reassemble the bits and reconstruct things that have fallen into the black hole. I think people
Yeah.
have proved that that is actually exponentially impossible because to do so requires so much computation power. So obviously, like a little box of gas is way less crazy than a black hole, but the same limit would apply. Like there's certain things that probably just won't be computable, or at least it won't be computable quickly enough for you to do anything about it. And in that sense, there will be a limit how much you can exploit this thing. But practically, where that limit is, I think it's a bit unclear. And it'll be interesting to see where the research leads for this.
I see. That makes sense. Yeah, so what you're saying is there's a limit to how much you can, do this, which is evidenced by black hole, physics, the work that people have done in that domain. Because you can't like fully reconstruct just anything willy-nilly that just, falls into a black hole. Even though like, I mean, we've talked about that the information or the possibility or whatever you want to call it is preserved. So in principle, like with a sufficiently powerful enough computer, I could do it, but it would just like the chances of me getting like I would need to wait a real is it a question like just waiting a really long time with a really like unimaginably powerful computer, or what is kind of the, I guess just want to understand that a bit more.
Yeah, I think people have shown that it will take exponentially long, so probably way longer than the age of the universe, for you to
Oh,
actually reconstruct something that fall into a black hole. But the black hole is the ultimate scrambling machine, you know.
uh,
But this is sort of the upper bound on how crazy things get scrambled.
I see. So if I really wanted to actually like come as close as possible to truly deleting something, I just throw it into a black hole and it'll get
Yeah,
scrambled
yeah,
up.
probably, yes.
Wow. Can you imagine a sci-fi book on that? Anyway, uh, so okay, so I guess what I had one more thought I wanted to bring up, but now it's kind of escaped me. Maybe not as much as it would if I threw into a black hole, but it's escaped me.
I think that information you just got more uncertain. This is the entropy
Yeah,
is increasing, I think.
yeah. I guess like would so you mentioned they've shown this in principle, like do you think, I mean, so it requires the use of like a quantum computer, or like what would it take to pragmatically implement this? Like, and what could be possible applications if you were to speculate?
Yeah. Well, let me just say that I'm not an expert for sure, but probably a quantum computer will be somewhat necessary. Although I don't want to hype up any of the quantum technology we have.
Fair
It's still nothing
enough.
compared to what actually will be useful. Yes,
Fair enough.
but probably for a non-quantum computer,
Mhm.
it just costs too much energy probably, because you have a classical circuit and that's just too wasteful. For quantum computer, and you have to understand how quantum computer works. Quantum computer actually becomes part of the thing that they are emulating, because we talked about many episodes ago. Quantum information is indestructible. Cannot cannot remove it. You can think of it as a fluid, which is a good way to think about it. So in order for a quantum computer to manipulate, let's say, a box of gas, the information fluid, by analogy, the information from the system has to actually go into the quantum computer. That gets manipulated, and an action shows up and does something to the system. So basically, the computer and the system become one. I guess this
Mm.
is, kind of got this like Matrix vibe or something. You gotta become one with the system to manipulate it. And so inherently, it's a very different process. You know, in some sense, less wasteful, because like the system is a computer. The computer is the system, right? Um, in terms of
Mm.
what I think will be achievable in the future, let's say 1 million years. Imagine humans survive and we become like a galactic empire, right? Uh,
Okay.
maybe you have fusion reactor engine warp drives that are super efficient, that will have to utilize some of that technology, right? Like quantum AI that are part of the engine, and that, I don't know, that extracts energy in the most efficient way, or close to it, by leveraging information and process them in the most efficient way through some AI network. Probably not even close to the AI that we have. So I don't know. Maybe good for a movie, but
That's fair. I really like how you threw the two words quantum AI. I like
yeah,
it.
maybe we'll get up a billion views on this video just because the quantum
Great
AI
title.
hype.
Quantum AI is here. Okay. Anyway, okay, I remember my question. Actually, it's partially informed through your previous answer you just gave right now. Um, like, can I just throw like a random quantum computer, assuming it works, doesn't need superconducting things. Let's suppose like quantum technology is sufficiently advanced where you have viable quantum computers. Can I just throw any quantum computer into the system, or do I need to configure it in a certain way, or how does that work?
Well, I imagine if you are able to to optimize this Szilard engine, if you were to optimize the Szilard engine to do the maximum amount of work, like I said, the computer has to become part of the system. You need some automatic reaction linked to the outcome of a computer. Yeah, basically, it's like there's this law in quantum computing that once you see the answer, you kind of destroy the answer. Yeah, because when you observe something, you have to do it destructively. So, but then you don't want that because you don't actually care about the result of the computation. You just care that the system react to it and extract energy out of it, right? So, so probably this wouldn't be so much of a quantum computer, but just like a quantum engine, I would say. But you know, it's got elements of quantum computers because it needs to compute and react in a quantum way. But I don't know what that looks like because we don't have it yet. But maybe in 1,000 years, that's the technology that we'll have. Who knows?
So I mean, we could just say a quantum system, not necessarily even like a computer, just a quantum system you kind of like implant it in, I don't know, in this like material, and you just let it go. And it just, there's no, I mean, yeah, there's a computation happening, but like, it's just doing what it's doing.
Right. You can think of it that way. Yeah. So maybe we just call it a quantum engine. You know?
Okay.
Yeah, and if it does work, I bet you, if it does work, you know, if this thing is true in principle, and if aliens exist, I bet you they'll be using this. That would be my guess.
So could I think of this as like, I have a quantum engine that's like made up of this specific specialized configuration of, you know, of quantum states or particles or whatever, and then I dump in some kind of like material or something, or maybe it's very different. Maybe I inject a quantum system into like another quantum system, and then I'm able to extract more work than I would have expected, like classically, let's say from like, you know, burning fuel or you know, whatever, moving a piston or whatever else. Is that fair? Is that fair to say?
Yeah, I think that's the hope. I don't think it's been demonstrated that this definitively works, but there's hope that maybe this could be the engines of the future, right? But who knows?
I see. No, that makes sense. I mean, yeah, I don't know if it'll be done in our lifetimes, but if it is, I'll be very thrilled.
I'll be thrilled too, I think.
And so there wasn't I guess there's an audience question, but before I get to that, because that seems to be a little bit of a more tangential direction, you know, we're basically almost at time at the episode, and want to, you know, in a tradition, Tim, leave the audience with any words of wisdom that this quantum AI has taught you.
You know, I think the one thing about physics is that physics is it's very funny. A lot of times, if interpreted properly, it almost feels like there's this life lesson in there. And today's episode's lesson, I think it really exemplified the fact that knowledge is power. And I mean literally, like quantum knowledge actually gives you power from the engines. So I would say, hopefully that motivates some people to learn. Not just for knowledge, but guess what? Knowledge can get you can really eke out something more than just the entropy or information decay of the universe. You know, this is the way to go. Knowledge.
I really like that. I really like that. Anyway, so I want to ask an audience question before we, you know, call it. Is I think this was to you and Mikey, but since Mikey's on here, you know, just your answer off to suffice. Do you guys still work as researchers during the day, if I may ask? That is the question.
Yeah, unfortunately we don't anymore, and honestly we were researchers for about a decade plus, and I think Mikey and we were researchers, and Sahil, you were in graduate school, also doing research in in past years of our lives. And that's the thing, in fact, if we were still researcher, we probably wouldn't be doing this. The life of a researcher is pretty strenuous, I would say, and we don't really have time to think about these things. But we work for the industry now, so as a result, at least personally, I think I probably can speak for Mikey. We have a little more free time, and we still love physics just as much as we used to when we were researchers. And we want to express scientific knowledge to everyone, and that's why we spend more time thinking about how to make some of these technical topics more accessible, to come up with analogies and whatnot. And that's the reason why you see this podcast, right? So unfortunately, we don't work as researchers in an academic sense, but we still try to keep up with some of these stuff that we have, these research level topic.
Yeah, no, great answer. Yeah, so on that note, I want to thank everyone for joining us, and we'll see you all next week.
Yeah, thank you all. Bye bye.